with my harness on. That's why I said I wanted to bring a lighter jacket along instead. A lighter shirt I planned to put on, but then I got distracted. What'd you say? Uh-huh. Oh. Oh well. I hope so. Does this have a battery? No? Not much. Lock the door.
1:25. You have 5 minutes.
Okay. I should have left these glasses in the car. Which way are we going? That way?
Same with perceiving.
They crash. Sí, para llegar en otro sentido. Con tu cara aquí. Acércate. Acércate. Trae la granitud más fácil a pintar. No, they crashed either. And then I tried to grab it.
Did you use the restroom?
It's outside.
Okay, anybody interested in 132 or it's starting in 1 minute? We'll be going up to the 4 meter. And it's free, so nothing to waste but your time. If anybody has trouble walking up there to the 4 meter, it's a pretty long, steep walk. You can get a permit up there at the front desk up there. I will open up for that. If you can't hear me back there, you can move forward if you want. All right, Kitt Peak, everybody. My name is Phil, and I'll be taking you up to the 4 meter telescope. Before you get too far along, if you have any cell phones, we'd appreciate it if you'd either turn it off or put it into airplane mode. We have a couple of radio telescopes up here, or just down the mountain a mile or two. They'll pick up your radio signals from your phone and think they've discovered ET or something, so if you shut that off, we appreciate it. The other thing too is when we're walking up to the 4 meter, there is a lot of traffic that goes up and down that hill there, and so we got to be careful of that. They can go kind of fast sometimes. So.
How many miles is it?
Oh, half a mile.
Not that
It's
far.
like this. So if you're not in good shape like you guys obviously are, for us old people, it might be a problem. So anyway, another thing too is we are up in an elevation of about almost 7,000 feet. So if you feel yourself starting to get a little woozy or something, get down on the ground or the floor before you fall down. We've had people do that, so my suggestion is get down. All right, Kitt Peak National Observatory. We have around 24 telescopes up here, not all of which belong to the National Observatory, but 3.4 of them do. One of which is the 4 meter telescope we're about to go look at. How does an astronomer get time on a telescope? Well, they need to submit a proposal. They can submit these proposals throughout the year, and twice a year these proposals are reviewed by what they call a time allocation committee. And if your proposal is accepted, you'll then get time on one of the telescopes up here. You might like fly into Tucson International Airport, get picked up by NOAO, brought up to the mountain here, familiarized with the cafeteria and the dormitories and everything, and then you'll get to go to your telescope later in the afternoon, where you might be working with a telescope operator or by yourself if you've already been trained on the telescope. And then as evening approaches, you'll go back to the telescope and start doing your observing. Now, what does this cost right now? National Science Foundation is covering the costs of most of everything up here, but that is changing. We are losing a lot of our funding to a lot of the newer, larger telescopes that I'll talk about here in a few minutes. So really all the astronomers are paying for right now is their room and board, which ends up being about $90 a night. Now, when they're up here during their 3 to 5 nights, if they're clouded out or rained out or too windy or whatever, that's just too bad for them. They just lose their time. So they will have a chance to submit their proposals again, and maybe they'll get accepted the next semester or something. Yeah. Okay, why do we have a national observatory, and how did it end up here in Kitt Peak? The reason why is we've got to go back to 1950. National Science Foundation was created. The National Science Foundation, or NSF, owns everything from astronomy to zoology. And back then they thought, the National Science Foundation thought it would be good to have a national observatory where anybody with a good idea, a good observing program would happen to have an opportunity to get on a nice, great big telescope. Up until that point, all the telescopes and observatories in this country were actually owned and operated by universities and funded by wealthy people, and like Carnegie Institute and that. So really just anybody couldn't get on them. So the idea was, with a national observatory, anybody with a good idea could get on a big telescope. So 53, a group of astronomers met up at Flagstaff to discuss this opportunity, and they ended up hiring a gentleman in 1955 by the name of Abe Meinl to come down here to the southwest to look at some spots and decide what kind of telescopes might be of value. So he came down here shot some rockets up at White Sands Missile Range, took some pictures because they didn't have Google Earth back then. Saw some potential sites, continued to winnow down those sites till he got down to 2 locations, one here on Kitt Peak and then the other one up in the Wallapai Mountains near Kingman, Arizona. Well, they put instrumentation up on top of these 2 mountains, and after looking at the data that they collected, they determined that both sites were about equable. You know, they were equal. What they were looking for in a good site was a site that had good seeing and good transparency. Seeing just means that you have a nice steady sky to look through, so the stars aren't twinkling like crazy. Sometimes, some nights you see stars twinkle like crazy. Well, that's not a good thing. Astronomers like nice steady stars. So that was something they were looking for. They're also looking for a site where they could really see faint stars in, and that's what they call transparency. So transparency is dependent on what's in the atmosphere, such as there might be smoke or pollen or dust or humidity. So you always try to find a site that doesn't have a whole lot of that junk in the atmosphere. That's one of the reasons why they like to stick it up on mountaintops, because you're above a lot of that junk, okay? So anyway, they looked at that data, both sites were about the same. They had some other criteria they'd set up too. They wanted a nice large mountain with a relatively flat top on it because they knew they were going to put a lot of telescopes on it. They didn't want to have to spend a whole lot of time and effort and money leveling the thing, blasting it flat. They wanted it somewhere around the 7,000 to 8,000 feet range. One reason being is they didn't want to have to deal with a whole lot of weather issues. Once you get up 9,000 to 10,000 feet, you're going to have to start shoveling snow and everything, and they didn't want to do stuff like that. They were looking for it near a modest-sized city with a good university system and airport. Kitt Peaks and Tucson situation. You know, Tucson did have the U of A, Stewart Observatory. It had the international airport there, so that was good. So anyway, they looked over this other criteria, and it turned out that Kitt Peak was probably the better site to build the National Observatory. So they said, okay, let's do that. One problem with Kitt Peak, though. Kitt Peak happens to be on the Tohono Reservation, and well, apparently the Tohono didn't mind the astronomers coming up with these little telescopes on the back of a horse and everything, but when the idea came out that they're actually going to have to tear a great big construction road up the side of their second most sacred mountain, and they're going to be putting these great big white observatory domes on it, they weren't so thrilled with the idea anymore. So what they did then was a gentleman down at the Stewart Observatory by the name of Dick Carpenter, he says, let's invite some of the elders of the tribe down here to Stewart Observatory on the campus, and we'll show them the night sky with a telescope we got down here, and talk to them, and they would talk them into letting us build up there. So they did that one night. It was a full moon night, and full moon nights, if you're an astronomer, whether you're professional or amateur, is really kind of a crummy night to observe. The full moon is the ultimate in light pollution. It kind of washes everything out. But they invited them down. They came down, looked through the telescope at the moon, maybe a galaxy or a planet or something, and talked to them. And before long, they actually had the elders convinced that it would be okay to go ahead and build up on top of Kitt Peak. So a contract was signed in perpetuity in 1958 for the grand sum of $25,000, which back then was probably a fair amount of money. And let's see, the observatory has around 220 acres of land on top here, as well as a 2,000 acre buffer around it. And annually, the tribe gets paid something per acre for that. If there's any job openings up here on top of the mountain, members of the tribe get first crack at it if they're qualified for it. We purchase electricity through them. They provide us with fire protection. There are some restrictions on what can be done up here. There can't be any commercial development up here, so no KFCs or Wendy's or anything like that. Can't be used for any military purposes either. No observation posts for like border patrol or anything. So that's kind of why we have a national observatory and how it ended up here on Kitt Peak. Okay. All right, a few things about telescopes before we go look at the 4 meters. Basically, there's 2 kinds of telescopes in the world. There's what they call refracting telescopes and reflecting telescopes. Refracting telescopes use lenses, kind of like what you might have in your glasses. So what happens, light from a star comes down, it goes through the lens, gets focused to a single point where you would have some kind of device, maybe even your eye, to look at a magnified object, image of the object that you're looking at. So that's what they call a refracting telescope. They have some problems with them, and the largest refracting telescope in the world is a 40-inch Yerkes refractor up in Williams Bay, Wisconsin. They can't make refracting telescopes any bigger than that because the lenses get so big and thick. They have trouble supporting them and everything, so the day of the large refractor is over with. So what they do nowadays is they build what they call reflecting telescopes. And reflecting telescopes use mirrors. Now the kind of reflecting telescopes we have up here on Kitt Peak are what they call Cassegrain telescopes. The way they work is that light comes down from a star or galaxy. It comes down through the tube of the telescope. It hits what they call the primary mirror. It bounces the light off the primary mirror up to the secondary mirror, and then from the secondary mirror it gets bounced down through a hole that's actually in the primary mirror. Now the primary mirror is what we refer to when we talk about a 2.1 meter telescope, a 3.5 meter telescope, or a 4 meter telescope, like the one we're going to go visit. That's the size of the primary mirror, okay? That's how astronomers generally refer to telescopes. Now, if you look over here, here's actually, I told you the core is cut out of the center of the telescope mirror. Well, here is actually the core of the 4 meter telescope mirror right there. That was cut out. Yep, that's the hole. That the light from the secondary mirror comes down. Now, another thing about telescope mirrors have to be grounded in a special way. They either have to be parabolic or hyperbolic. If they were strictly spherical, what would happen? If it was strictly a spherical mirror, this light, when it bounced off, would come to focus at a whole bunch of different points, okay? And we can't have that. We have to have the light come focused back to a single point, if it's parabolic or hyperbolic. So that's what's happening here, and it's bouncing off this light, off this mirror, which is also a parabolic convex mirror, and rolls it down through that hole where the detectors are. Yes, sir?
Isn't there also another type of reflector where the center is flat, that's tilted, and the eyepieces on the side?
That's a Newtonian. Yeah, that's very common in amateur telescopes. That's not too common in professional scopes, although the telescope that was originally down on the U of A campus, Stewart telescope, actually was one of those until they moved it up here and then they changed it around some. But yeah, that was a Newtonian, which is very unusual for professional telescopes. So anyway, now one thing about these telescope mirrors is they all have a shiny material on them, aluminum, okay? Very thin layer of aluminum. You can kind of see how these are shiny here too. They got an aluminum surface on it that's been laid on it that's probably about 1,000th the thickness of a human hair. So it's a very, very thin layer. And on occasions that layer has to be, it gets dirty and it gets cleaned off, but then it gets to the point where it gets so tarnished and thin that they actually have to re-illuminize the mirror, which means that they take it out of the telescope and remove the old aluminum surface and then stick it in what they call a vacuum deposition chamber where a new layer of aluminum is laid on it then again. So that's kind of how that works. So this is kind of how telescopes work today. Telescope mirrors that they made back then were when they first started making telescope mirrors, they actually ladled glass into a big form, you know. Unfortunately, when you started getting the bigger mirrors, there were a lot of bubble problems that would be created, so they went to a different method called a sagging method, which involved putting chunks of glass on top of a ceramic pylon-like, and then they would heat the whole thing up, and the glass would then just kind of form and melt and form inside the form, which is how the 2.1 meter telescope is done. And then when it came to the 4 meter telescope that we're going to go visit, it actually consists of a number of ingots. So they had these glass ingots that are 6-sided, and they would put all these together to make the bottom section, and then they would heat it up and it would melt and it would all kind of form together. Then they did another layer of these like 6-sided ingots that were about so thick, and made the second layer. Then they finally made the top layer of this mirror out of some bigger ingots, probably about sole by sole. You can actually see how that thing is layered up there. And so they would put those together and heat it up, and then finally you would end up with a telescope mirror that was, flat on the top. And then, of course, if it's flat on the top, that means that the mirror has to be ground. And that, using the old methods, that would take 1.5 or 2 years to grind that parabolic shape into the surface of the mirror, because you'd be literally grinding away hundreds and hundreds of pounds of glass. And of course, that would take a long time to do that, until finally you got your perfectly hyperbolically shaped mirror surface, and then you would have to go in and inlay that layer of aluminum on it again and make yourself a telescope mirror. Now, today they make telescope mirrors in some really interesting and unique ways. The University of Arizona Stewart Optical Lab does it one way, and they make large mirrors using what they call a spin cast method. And those kinds of mirrors can be made up to 8.4 meters in diameter, so they can get really big. The 3.5 meter telescope we have up here, it's referred to as the WIN telescope, W-I-Y-N, is actually a spin cast type mirror, and it was one of the first ones ever made. But the way the spin cast telescope mirrors are made is they have this form, and you'll say it's 8.4 meters in diameter, and there's a honeycomb structure all inside of that thing. And this over here gives you some kind of idea of what it looks like. So it's all honeycomb. What they will do is they will actually put big chunks of what they call borosilicate glass, kind of like a pirate, on top of this form, okay? And they stick it in this oven, and there's literally thousands of these pieces of glass that are put on there. So they pop it in the oven, put the lid on it, and start raising the temperature up on it to a couple of thousand degrees. Then when it starts getting to about the consistency of cold honey, they will actually start spinning this oven, about 6 revolutions per minute. And by doing that rotation thing there for days, what ends up happening is that liquid glass that's in there actually forms a parabolic shape to it, kind of like if you're spinning a glass, and you spin a glass, it'll actually form a parabolic shape of the liquid in there. So they claim that's kind of how they got the idea to do this. So anyway, that glass all spreads out on top of the form there and goes in between these honeycomb things here. It doesn't go in them, it goes in between them. Then there's also about a 2-inch thickness of glass on top of that. And that's what they then use to do their final grinding and polishing with. So it takes a lot less longer to make big telescope mirrors using a spin cast method than when you had to start out with a flat top on it and grind it all down with machines and everything. So now some of the big telescope mirrors they're making, they've made one called the LSST mirror down there, which is an 8.4 meter. That telescope mirror is going to be located in Chile. Its LSST stands for Large Synoptic Survey Telescope. That thing is going to be looking at the night sky about every 4 days. It's going to be able to go around to get back to the same spot that it started at. So it's going to actually be able to take movies of the night sky almost in real time, and all this data is going to be available to anybody to go online and look at it. In fact, every night the telescope is going to create about 30 terabytes of data every night. So right now, there isn't enough storage space in the world to handle all the data that this telescope is going to produce during its lifetime. So they're actually building server farms to store the data on this thing. So that's a really neat, cool telescope that's going to be maybe in the next 5 or 6 years. Also down at the Stewart lab, they're working on the Giant Magellan Telescope, GMT, which is going to consist of 6 of these great big 8.4 meter mirrors, like one there, one there, in a circular thing. Then with one 8.4 meter in the very center, and to produce, I don't know how many meter telescope that is, but it's going to be a really big telescope. And so the Stewart Optical Lab has made like three of those mirrors already, so they got about another 4 more to go. That probably won't be ready to run for about another 10 years or so. Then there's also a 30 meter telescope that's I think they're just breaking ground down in Hawaii. And this is going to be a segmented telescope where you're going to actually have segments. So probably, here's a good idea what the segmented mirror is going to look like. So these are about 1 meter in diameter or something like that. So the whole 30-meter mirror will consist of all these segmented mirrors in it, rather than just one monolithic one. So that's another way they make telescope mirrors. There's another kind of mirror that's called the Gemini telescopes. There's Gemini North and South that belong to NOAO. Gemini North is in Hawaii and Gemini South is in Chile. But those are all I think they're 8-10-meter telescopes. But they were all made using a method that they call a meniscus method, where they would actually take a piece of glass, I don't know, so thick or so, and they would lay it on this form, and then what they would do is they would actually heat it up, and then they would draw a vacuum on the back of it, and then that would create the mirror form that they wanted. So there's different ways of making telescope mirrors. The key to the new ones that they're making nowadays is the fact that they're big, but they're also very light. If these telescope mirrors were made the old-fashioned way, well, the 4-meter we're going to go look at weighs around 33,000 pounds. So like an 8-meter one would, let's just say, it would weigh 66,000 pounds. You know, so that's awful heavy. And if you had telescope mirrors that big, it'd be really difficult to build any kind of mounts to actually move those massive mirrors around. So with the advent of these new telescope mirror making methods, we're actually able to have much lighter telescope mirrors, and we can use much smaller, lighter mounts to actually move them around on. They're called what they call alt-azimuth mounts, and as opposed to the equatorial mount that you'll see when we go out and look at the 4-meter. Okay, so that's kind of what's happening with the new telescopes, and it's going to be really interesting and exciting when they get these things open, but unfortunately we do lose a lot of our funding up here from the National Science Foundation because they have putting all their money in these big new fancy telescopes, but that's the way it is. Yes, sir?
Are there going to be any more new telescopes here?
Up here? Probably not. Nope, they build all the new telescopes get put down in the Atacama Desert in Chile because they got really high mountains there and the air is really dry. That's another thing astronomers like is really dry air. They don't like a lot of moisture or humidity in the atmosphere because the more moisture and humidity in the atmosphere, the more difficult it is for you to do near-infrared imaging. Now, near-infrared is that portion of the electromagnetic spectrum just barely out of our ability to see on the red end of our sight. You know, we can see green, yellow, green, blue. We can see red, but then there's a little spot in the electromagnetic spectrum just beyond what we can see in the red that's called near-infrared. And we have all sorts of cameras and stuff that can pick that kind of stuff up. Our eyes can't. But so if there's a lot of moisture in the atmosphere, that kind of near-infrared information gets kind of filtered out through the moisture in the sky. Oh yeah, then the other telescopes will always be being put up in Hawaii too, up on Mauna Kea. So those are the two primo spots. That and space, but there's not too many going up in space, other than the Herschel. What's that?
There's a James Webb.
Yes, the Webb telescope. That's the next
The
one.
mirror on that looks like that. Yeah,
Yeah, that's the LSS2. Yeah.
How big is the mirror for that one?
For the which one?
James Webb.
That might be around 8 meters, something like that. It's bigger than what's up in the Hubble.
Yeah, Hubble's like a 3.
But that's a whole different kind of telescope.
Yeah.
That's really intended for a lot of infrared imaging and stuff. Okay, we ready? All right, if you need to get a permit to drive up there, go see if there's anybody up there to talk to. Otherwise, we'll walk up. We'll make a few stops on the way up. So if you're in reasonable shape, you might be able to make it.
Can you use the restroom? So you can use it. You can use it.
You know, they've been told that
It just means it's made for everybody.
we just talked to them and tried to convince them that they shouldn't, there's regulations and everything that kind of keeps it at bay somewhat. Okay, the wind telescope I talked to you about is this silvery looking one right up here. So that has the 3.5 meter spin cast area. It also has what they refer to as a spin cast. That weighs about 4,000 pounds, 3.5 meters, whereas the 4 meter telescope we're going to go look at now, the telescope's weight on that one goes around 33,000 pounds. So you can see that there's a considerable difference. This one was built in 1993. It's probably going to be the last